Hi everyone, hope you all doing well. Today we're going to explore more about relations. That is one of the important topic from discrete mathematics. I am Ragavilashni Raja going to guide you on for part 1.1 of topic relations, which covers the introduction to relations and some of its properties such as reflexive, symmetric, transitive and anti-symmetric. Are you ready for this? Let's do it. Let's consider that set A consists people named Bala, Chong, Ali, and set B consists people named Muthu, Susan, Hamad, and Abu. The relation we set for these sets is cousin of. The relation R will be Bala is cousin of Muthu, Chong is cousin of Susan, Ali is cousin of Ahmad, and Ali is cousin of Abu. So from here we can clearly see that the relation R is subset of set A cross set B. From here we can conclude that relation is as here. If A and B belongs to R, then A related to B by R. And if A and B not belongs to R, then A and B is not related. From here, we can define relation as a connecting tool of one object to another, just how we identify a relation of a person to another in our daily life. Now, move on to properties of relations. The first property is reflexive relation. Reflexive relation defined as a relation R on set A is said to be reflexive if every element of A is related to itself. R is reflexive if and only if A, A belongs to R and A belongs to set A, means that A related to A. For example, let's consider set A consists elements 1, 2, and 3. And the relation A has 1, 1, 2, 2, 3, 3. This relation is reflexive to set A because 1 is element of set A and 1 related to 1. Same goes to number 2. 2 is element of set A and 2 related to 2. 3 is element of set A and 3 related to 3. The second property is symmetric relation. A relation R on set A is said to be a symmetric relation if and only if AB belongs to R implies that BA belongs to R for all A and B belongs to A. Simply, we can say that A related to B implies that B related to A for all A and B belongs to A. For an example, let's consider set A contains element 1, 2, 3 and 4 and relation 1 which is R1 is 1 and 3, 1 and 4. 3, 1, 2, 2, 4, 1. This relation, which is R1, symmetric relation on A because it follows all the rules that we discussed earlier. Here we can see that 1, 3 belongs to R1, 3, 1 belongs to R1, 2, and here 1, 4 belongs to R1 and in reverse way 4, 1 belongs to R1. 2, 2 belongs to R1 and in an opposite way they also belongs to R1. It can conclude that the R1 is symmetric relation on A. The third relation that we're going to discuss is transitive relation. It's defined as let A be any set. A relation R on A is said to be transitive relation if and only if A and B belongs to R, and B and C belongs to R implies that AC belongs to R. For all A, B, C belongs to A. Simple as that, we can say that A related to B, B related to C, A related to C. For all A, B and C belongs to A. For an example, let's consider that set A consists of elements 1, 2, 3 and 4 and relation R1 is 2 and 2, 1 and 1, 3 and 2, 2 and 3, 3 and 3. And as we said earlier, A and B must be belongs to R and B and C must be belongs to R. So just compare the ordered pairs 3 and 2 and 2 and 3. We know that both are belong to R. Thus, the AC, which is 3, 3, belongs to R. So we can conclude that R is transitive relation on A. The last relation for our session is antisymmetric relation. Let A to be any set. A relation R on set A is said to be antisymmetric if and only if A and B belongs to R and B and A belongs to R implies that A equals to B. For all A and B belongs to A. For sure, you guys need an example to understand this. Let's consider set A consists elements of 1, 2, 3 and the relation R is 1 and 1, 2 and 2, 2 and 3 and 1 and 3. If R is antisymmetric, it must satisfy this rule. 1 and 1 belongs to R. If we interchange both x and y coordinates, we get BA, that is 1 and 1, which implies A equals to B, which is 1 equals to 1. There is also another ordered pair, which is 2 and 2, which satisfy antisymmetric rule. Thus, we can conclude that R is antisymmetric relation to A. That's all for part 1.1. Hope by now you guys understand what is relation and some of its properties. Let's continue to another part.
Hello guys, today I'm going to talk about partial orders. So let me get into the topic. There are three types of partial orders. The first one is antisymmetric, second is reflexive, third is transitive. Antisymmetry. If two objects are both related to each other, they are same object. A in relation to B or B in relation to A equals to B. So thus, both values are the same. We often confuse with antisymmetric and symmetric. Symmetric happens when if X relation to Y, then Y not relation to X. It's called symmetric. In this example, we have to find the antisymmetric relation. So we know that set A consists of 1, 2, 3, 4. So antisymmetric, which is mean by both objects are same. So in this content, 1, 1, 2, 2, 3, 3 and 4, 4 will be the relation to antisymmetric. Reflexive relation is a relation where the one in which element maps to itself. For example, consider set A, 1 and 2. Now the reflexive relation will be R equals to 1, 1, 2, 2, 1, 2, 2, 1. Okay, we know that X relation to Y, if and only if it satisfies the equation divisible by 5. So from here, we know that we consider X subset of A, so it satisfies the equation above, Therefore, X relation to X holds for all X in A. Hence, R is reflexive. Okay, we know that transitive is comparing from element to element. Like if we have a set of consists of three elements A, B, C. Uh, so when R relates to A to B and B to C, then R also relates to A to C. So from example below, when X equals to Y and Y equals to Z, so thus Hayes diagram is a graphical rendering of a partially ordered set displayed via the cover relation of the partially ordered set with an implied upward orientation. We will look deep into this in the next slide. There are four steps to convert to Hayes. The first one is draw a directed graph so that all arrow points are upwards. Second is eliminate all self-loops. Third is eliminate all arrows implied by the transitive property. Fourth is remove the direction of all arrows. Over here you can see the example of a Hayes diagram shown below. This is a convention of using an undirected line, the poset relation. So hence the ordering elements is read from bottom up.
Today I want to talk about equivalence relations. At first, the definition of equivalence relation. A is relation on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. Two elements that are related by an equivalence relation are called equivalent. If A are B, then A is equivalent to B, denoted by this. The properties of equivalence relation. The first, R is symmetric. A is equivalent to B whenever B is equivalent to A. Can write like this. AB is belong to R. A is belong to A. B is belong to A. Then BA is belong to R. The second, R is flexive. Every element is equivalent to itself. For all A R belong to A, then AA is belong to R. The third, R is transitive. If A and B are equivalent, B and C are equivalent, then A and C are equivalent. A, B, C are belong to A. AB is belong to A. BC is belong to A. Then AC is belong to A. The second part, equivalence classes. The definition of equivalence class. Let R be an equivalence relation on a set A. The set of all elements that are related to an element A of A is called the equivalence class of A. Notation by this. Denote this for equivalence class if only one relation is under consideration. For all A R belong to A, the equivalence class of A is equal to X. X is belong to A. Conjunction ARX. The partition of equivalence class. Let R be an equivalence relation on set A. A, B, C are belong to A. The first, the equivalence class of A is not equal to empty relation. This is not empty set. This means empty relations. Because A is belong to the equivalence class of A. The second, if AB is belong to R, the equivalence class of A is equal to the equivalence class of B. If AB is not belong to R, then the interaction of equivalence class of A and the equivalence class of B is empty set. That is, the equivalence classes of non-equivalent elements do not intersect. The fourth, the union of the equivalence class of X is equal to A. That is, the union of equivalence classes of all the elements in the set A is equal to A.